Besides trigonometric, exponential, and logarithmic functions, there is also another type of transcendental function called hyperbolic. What are they, and how are they differentiated? Learn it here in differential calculus. What are hyperbolic functions? These are similar to trigonometric functions, although they are referred from hyperbola instead of a circle. The two main functions are also defined with exponential functions. Hyperbolic sign is given as half of e raised to x minus e raised to negative x. E is Euler's number. Hyperbolic cosine looks very similar with the previous function, with just a different operator. Hyperbolic cosine is half of the summation of e raised to x and e raised to negative x. The other functions are based on trigonometric identities, such as hyperbolic tangent, which is then taken as hyperbolic sine over hyperbolic cosine. This is also taken as the reciprocal of hyperbolic cotangent. Then hyperbolic cotangent is hyperbolic cosine over hyperbolic sine, and also 1 over hyperbolic tangent. The other two functions are hyperbolic secant, which is same as the reciprocal of hyperbolic cosine, and hyperbolic cosecant, which is also equated to the reciprocal of hyperbolic sine. In this video, we are to differentiate the hyperbolic functions starting with hyperbolic sine of x. Again, sine h of x is half of the difference of e raised to x and raised to negative x. The term can be differentiated separately. So factor out 1/2, then place d over dx over each term of the difference. The derivative of e raised to x is e raised to x with d over dx from chain rule. The next term is solved similarly. The derivative of e raised to negative x is still e raised to negative x with the attached d of negative x over dx from chain rule. Now dx over dx is 1, and d of negative x over dx is negative 1. Simplifying the right term into half of e raised to x plus e raised to negative x. Half of e raised to x plus e raised to negative x is also just mentioned as hyperbolic cosine. So the derivative of hyperbolic sine x is then hyperbolic cosine of x. The derivation of the derivative of hyperbolic cosine is similar with that of sine. Start with the exponential equivalence of hyperbolic cosine, which is half of the summation of e raised to x and e raised to negative x. Take the derivative of each term, placing 1/2 out, then work with d over dx of e raised to x, which is still e raised to x, then attach chain's rule d of x with respect to x. The second term is differentiated similarly, giving e raised to negative x, then attach d of negative x over dx. The first chain rule term is equated to 1, and the second is negative 1. Simplifying the whole term into half of e raised to x minus e raised to negative x. This is the exponential form of hyperbolic sine. Thus, the derivative of hyperbolic cosine is hyperbolic sine. To derive the derivative of hyperbolic tangent, use the identity that tangent is sine all over cosine. By quotient rule, the derivative then turns into the square of hyperbolic cosine in the denominator. The numerator has low d high minus high d low rule. That's low term of hyperbolic cosine with d of high which is hyperbolic sine. Subtract the term with high of hyperbolic sine with d of low hyperbolic cosine. The first term then can be solved by starting with the copied hyperbolic cosine, then the derivative of sine is cosine, with chain rule of dx over dx. The second term starts with the copied hyperbolic sine and the derivative of cosine, which is sine, then attach dx over dx. From the two terms, dx over dx is cancelled out to 1. Simplifying the terms into the square of hyperbolic cosine minus the square of hyperbolic sine all upon the square of hyperbolic cosine. The numerator can then be further simplified into 1 from the hyperbolic identities, thus creating 1 over hyperbolic cosine square. This is then converted as the square of hyperbolic secant, bringing about the pattern for the derivative of hyperbolic tangent as the square of hyperbolic secant. Hyperbolic cotangent is also taken as hyperbolic cosine over sine. Taking the derivative of the ratio requires quotient rule, where the denominator is the square of hyperbolic sine. The numerator then observes low d high minus high d low pattern, starting the hyperbolic sine times the derivative of hyperbolic cosine, then subtract hyperbolic cosine times d of hyperbolic sine. This then can be processed as hyperbolic sine with another hyperbolic sine, then attach dx over dx. The second term starts with hyperbolic cosine with another hyperbolic cosine, then also attach dx over dx. Those segments from chain rule are simplified to 1, leaving the right term as the square of hyperbolic sine minus the square of hyperbolic cosine all upon the square of hyperbolic sine. Swap the terms in the numerator and introduce a negative sign. Then simplify the two terms into 1, making negative 1 over hyperbolic sine squared. This reciprocal is then transformed into the square of hyperbolic cosecant, thus the derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. Moving on in deriving the derivative of hyperbolic secant, this function is equal to the reciprocal of hyperbolic cosine. So since we have a rational expression, we use quotient rule once again. The denominator is the square of hyperbolic cosine. Then the numerator starts with hyperbolic cosine times the derivative of the numerator, which is 1. Subtract the numerator of 1 times the derivative of the denominator, hyperbolic cosine. From the first term, the derivative of a constant is 0. Then the derivative of hyperbolic cosine is sine with dx over dx from chain rule. Again, dx over dx is 1, simplifying the expression further into negative hyperbolic sine of x all over the expanded square of hyperbolic cosine. We expand the denominator in order to pair up 1 with the numerator, creating hyperbolic tangent. So, the right term then becomes negative 1 over hyperbolic cosine with hyperbolic tangent. The other term, 1 over hyperbolic cosine, is also simplified as hyperbolic secant, thus ending with the derivative of hyperbolic secant as negative hyperbolic secant with hyperbolic tangent. The last function is hyperbolic cosecant, where the differentiation is similar with secant. Use the equivalence of hyperbolic cosecant with the reciprocal of hyperbolic sine. Using quotient rule, we get a denominator of the square of hyperbolic sine. The numerator has hyperbolic sine with d over dx of 1, minus 1 with the derivative of hyperbolic sine. The derivative of a constant is 0, reducing the term into negative hyperbolic cosine times dx over dx all over the square of hyperbolic sine. Dx over dx is 1, creating negative hyperbolic cosine over hyperbolic sine with another hyperbolic sine. Pair one denominator term with the numerator and come up with hyperbolic cotangent, and the remaining term is negative 1 over hyperbolic sine. And this is also converted into negative hyperbolic cosecant. So the derivative of hyperbolic cosecant is negative hyperbolic cosecant with hyperbolic cotangent.